Hello everybody, welcome back to Math 251. Hope you're having a fantastic day. This is section 3.2's lecture video. Today's mathematician of the day is Benjamin Banneker, who was an 18th century black mathematician who invented the clock that chimed every hour. So it's pretty cool to think about how math was involved in something like a clock. Pretty neat. And did you know that Chinese mathematicians were the first to accept the concept of negative numbers? In many cultures, negative numbers were considered blasphemy. In fact, people were killed over their belief in negative numbers in other cultures. So, aren't you glad we live now where we can talk about negative numbers and not be killed? All right, today we will introduce the concept of a derivative as a function. So last time we introduced the concept of a derivative in terms of the tangent line at a certain point of a function. Today we are going to talk about how a derivative can be a function instead of just a slope. So the derivative of f of x is the function f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. We also introduced the definition, the limit as x goes to a of f of x minus f of a over x minus a. These two expressions are mathematically equivalent to each other, and we can use either one of them whenever we would like. Of course, this is the derivative if the limit exists and x is in the domain of f of x. If f prime of x exists, we say that f is differentiable at the point x, and if f is differentiable at every point in an interval I, we say that f of x is differentiable on I. So let us use this definition to find the function of the derivative negative x squared plus 3x. Now I want to pause here real quick. I know that some of us have taken calculus before, either in high school or maybe previously in college, and you may be looking at this function and thinking, well, I know exactly how to do that, I know all the rules, it's going to be way easier the way that I do it. And that's fine, and you can use those rules to check your work, but if a problem asks you to use the definition of the derivative, even if you know how to very easily find the derivative of the function, you do have to use the definition if it asks you to use it. So just a note on that. So let's use this definition to find the function of this derivative. So I'm going to use the first definition, the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so this becomes the limit as h goes to 0. Wherever I see an x in my function f, I'm going to replace it with x plus h for this first term. So this becomes negative x plus h squared plus 3 times x plus h. This is f of x plus h minus f of x, which is negative x squared plus 3x. All of this over h. Okay, well, if I expand the first term, this gives me the limit as h goes to 0. And then this gives me negative x squared plus 2xh plus h squared plus 3x plus 3h plus x squared minus 3x. All of this over h. Okay, well, now I can cancel some things out. So let's see what I can cancel. I see that this positive 3x cancels with this negative 3x. And I also see that this x squared cancels with this negative x squared. And I think that's all I can factor. So not forgetting about this negative sign here, this becomes the limit as h goes to 0 of negative 2xh plus h squared plus 3h over h. And now I can factor out an h out of every term in my numerator. So this becomes the limit as h goes to 0. If I factor out an h from every term on the top, I get h times negative 2x plus h plus 3 over h. And now it's that magical moment when the h's cancel. So I am left with the limit as h goes to 0 of negative 2x plus h plus 3. Now I can simply plug in my h value, which is 0, and this becomes negative 2x plus 3, which is our derivative. If I wanted to find the derivative of our original function at a certain point, x, then I would simply plug that x value into this new derivative function. Same thing with a tangent line or a slope. I would just plug in that x value into this new function. So this is the derivative function. That means that the slope of the tangent line everywhere is equal to negative 2x plus 3 of our original function, negative x squared plus 3x. So just a note on notation. I know that the textbook might use different notations than the online homework or this lecture, these lecture notes. So just to make a quick note, the notations f prime of x, dy dx, and d dx of f of x all mean the same thing. They all refer to the derivative of f of x. All right, let's do another example, this time with square root function. So we want to find the dy dx, or the derivative function. And this time we also want to find a tangent line at a certain point. So again, I'm going to use the first definition of the derivative function. So I'm going to take the limit as h goes to 0 of f of x plus h minus f of x over h. So wherever I see an x in my original function, I'm going to replace it with an x plus h. So this gives me the limit as h goes to 0. F of x plus h will be the square root of x plus h plus 1. I replaced that x with an x plus h minus f of x, which is square root of x plus 1 over h. Well, here in the numerator, I see that I have a square root minus a square root. And the best way for me to simplify this, hopefully you are aware of this trick, is to multiply by top and bottom by the conjugate of the numerator. So the conjugate will be the same two terms except with a plus sign in the middle. So I'm going to multiply the top and the bottom by the square root of x plus h plus 1 plus the square root of x plus 1. This will make my square roots in the numerator disappear over the same thing, x plus h plus 1 plus square root of x plus 1. So I multiplied this fraction by the conjugate of the numerator, and when I do that, all of my square roots in the numerator disappear. So I am left with the limit as h goes to 0. In the numerator, I will have x plus h plus 1 minus x plus 1, because when I FOIL this out, the inner two terms disappear. All of this over h times square root of x plus h plus 1 plus square root x plus 1. Well, some stuff cancels on the numerator. This negative x cancels with this positive x, and this negative 1 cancels with this positive 1. So I'm just left with an h on top. The limit as h goes to 0 of h over h times square root x plus h plus 1 plus square root x plus 1. Well, check it out. This h cancels with this one. And I am left with the limit as h goes to 0 of 1 over square root x plus h plus 1 plus square root x plus 1. And now when I plug in h equals 0 in the denominator, I no longer get 0 in the denominator. So if I plug in h equals 0, this gives me 1 over square root x plus 1 plus square root x plus 1, which is the same thing as 1 over 2 times the square root of x plus 1. So this is f prime of x. This is our derivative or our slope at any point on our function f of x equals square root of x plus 1. Now I want to use this function to find the equation of the line tangent to our original function at the point 3, 2. So I know that this function right here gives me the slope. So now to find the slope at a point, I simply plug in that x value. So tangent line, actually, you know what, let's say m sub tan is equal to, so I plug in our x equals 3 into what I just found for f prime, since f prime of x represents the slope of our function. So I say 1 over 2 square root, plug in that x equals 3 plus 1, which is 1 over 2 times square root of 4, which is 1 over 2 times 2, or 1/4. So that is the slope of our tangent line. And then to find our b value, our y-intercept, I simply plug into y equals mx plus b. My y value is 2. My slope is 1/4. My x value is 3 plus b. So this gives me b is equal to 5/4. So my tangent line is y equals 1/4 x plus 5/4. We simply plugged in our x value into our f prime of x function in order to find this. So let's see what this looks like on a graph. I want to, y equals square root of x plus 1. So that is my original function. And I am at the point 2, where was I? Oh, at the point 3, 2. So I am wanting to find the tangent line here at 3, 2. And when I plug in my tangent equation that I found, 1/4 x plus 5/4, check it out. At the point 3, 2, these two lines intersect each other, and my tangent line just brushes up against our red function at that point 3, 2. Pretty cool, huh? All right. So in the next example, we are going to use the concept of a derivative and to sketch the graph of f prime of x from the graph of f with this as f. So remember, f prime of x represents the slope of f of x. So I want to graph the slope of this function here. Sometimes like in the next example, we won't be able to tell the exact slope and we'll just have to estimate it. But here we can calculate the slope pretty easily. So I see that on this first chunk right here, my slope is -1. -1. So if I were to graph the slope, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So from the point 3, 4, 5, -5 to -3, my slope is -1. Yeah, -1. So here, from 5 to 3, my slope is -1. You will always want to use open circles. We will actually get to this in a minute, but at the endpoints of this, we are going to use open circles because our slope at the point through -3 here is not equal to -1. Again, we'll talk about this in a minute. Okay, next we have this chunk, and we see that the slope here is +1. So from -3 to 0, my slope is 1. So my y value here on this graph of f prime of x is equal to 1. In this next chunk, my slope is -2. So I have a y value of -2 from 0 to 3. And then finally, on this last piece, my slope is 1/2. So maybe somewhere like this. Oops. Again, I'm going to talk in a minute about why we use open circles at the endpoints. So this is how f prime of x and f of x are related. If you can calculate the slope easily, then your graph of f prime of x will look something like this with the straight bars, kind of like a piecewise function. That is what your graph of f prime will look like if you can calculate the slope easily. In the next example, we have this quartic equation, so we can't easily calculate the slopes. It would be impossible. So we're just going to have to draw a rough estimate of g prime of x. So let's see, I have 1, 2, 3, 1, 2, 3, and then I have 5, 10, 15, all of these guys. All right, so the first thing I want to do is figure out where my slope is equal to 0. So if my slope is equal to 0, and I were to draw a tangent line, then that tangent line would be a horizontal line. So I want to try to find where my I want to try to find where my tangent lines are horizontal. So if I look at this point right here, if I draw the tangent line, it is horizontal because this is a maximum or a minimum value, right? So the slope on this piece right here, it's negative, it's negative, it's negative, and then it gets really, really, really small negative, and then it turns to a positive slope. So at that minimum value, my slope is equal to 0. So that's at -2.5. So at -2.5, my slope is going to be 0. My y value will be 0. I also have a slope of 0 here. If I were to draw the tangent line, it would be horizontal. So I have a slope of 0 at this point, which is like -0.5. So at -0.5, my slope is 0. And again here at 1.5. So that gives me 3 points on my graph of g prime. So that's my first step when I can't calculate the slope, is to find where my slope is equal to 0. All right, next I need to look at where my slope is positive and where my slope is negative. So if I look at this chunk here, my slope is negative. I don't know what negative number it is. It looks like a pretty big negative number, but my slope is negative there, right? As I go to the right, my function moves downwards. So my y values here on the graph of g prime are going to be negative, from -4 to -2.5 right here. So I will look something like this. On this next chunk, from -2.5 to -0.5, here my slope is positive. As I move to the right, my function increases. So on this chunk, I will have a positive slope. However, we need to be careful about how we draw this positive slope, because as I approach this point right here, negative 0.5, it's going to be negative on the other side of that. So my positive slope will look something like this. My y values are positive here, but I know that once I get to negative 0.5, my y values will turn to negative since I have a negative slope here. It doesn't matter that on this piece right here, actually, let me draw in blue. It doesn't matter that on this blue piece right here, I am increasing and then decreasing. All that matters here is that my y values are positive, since on this blue piece over here, my slope is positive. Next, let's look at this little red section right here. Here, our slope is negative, so my y values over on the graph of g prime will be negative. So something like this. And finally, we have this last chunk here where my slope is positive. So that's why on this red piece, I had to come up back to 0, because now I am positive again. So my y values will be positive. So actually, it doesn't have little arrows, does it? So I just draw open circles at the ends. So this is what the graph of g prime looks like. Again, if you are struggling with this kind of concepts, I would watch this example again and maybe come to the Zoom sessions and ask for more examples of this graphing of g prime, or the derivative of a function. Because we just have to remember that the slope is equal to the derivative. So that is the key concept here. All right, at the beginning of this week, we talked about what it means for a function to be continuous, and several people asked, well, why does it matter? Why do we care about continuity? Well, we have this theorem that tells us why continuity is so important. So this theorem says if f of x is differentiable at the point A, then f of x is also continuous at A. Alternatively, if f is not continuous at A, then f is not differentiable at A. So what does this look like? Well, we have 3 situations. My first situation is if f is not continuous at A, then f is not differentiable at A. So let's draw a function here, something like this. Well, clearly at the point A, we're not continuous. So this theorem says that because f is not continuous, f is not differentiable at the point A. So let me write that down. F is not continuous at A. Therefore, by this theorem, it is not differentiable. Okay, we can have situations where f of x is continuous but not differentiable. So this is important because the converse of this statement here is not true. This theorem does not say if f is continuous, then f is differentiable. This theorem does not say that. So we can have situations where I am continuous but not differentiable. And we're going to talk about that down here more. But one example is if I have a corner at the point A. So if this is A, then f is continuous, right? We never break continuity, but I am not differentiable at the point A. That's because my slope coming from the right and my slope coming from the left are 2 different numbers here, right? If this was a straight up absolute value function, here the slope would be +1, here the slope would be -1. So my 2 slopes don't match up on the right and the left side of A. Therefore, this function is not continuous at A. Excuse me, not differentiable at A. So f is continuous here, but it's not differentiable. Another example of continuous but not differentiable we have is if I have a vertical tangent line, which looks something like this. So if I'm really bad at drawing these, but I'm going to give it a try. So if I have, for example, the cube root function, and I have like a vertical tangent line, this is y is equal to the cube root of x. So if I call this point right here a, then the limit as x approaches a from the left is equal to positive infinity. So limit as x approaches a from the left of this function is positive infinity, since this slope right here is getting really, really big. But as x approaches a from the right, my function here goes to negative infinity. So that's why I am not differentiable at that point. So here f is continuous, but not differentiable. So this leads to the question, when is a function not differentiable? Well, I'm so glad that you asked. A function f is not differentiable at a if at least one of the following conditions hold. F is not continuous at a. If f is not continuous, by this theorem, it's not differentiable. So if f is not continuous at a, then it's not differentiable because of the theorem above. Oops, I can spell theorem. If f has a corner point at a, it's not differentiable. Or if f has a vertical tangent. We did these two examples above. So these last two, B and C, these are examples of when I am continuous but not differentiable. So again, this theorem does not say if f is continuous, it is differentiable. The only thing that it says is if f is differentiable, it's continuous, and if f is not continuous, then it is not differentiable. So let's look at this last example. And actually, I want you to pause this video and try this example by yourselves first. We want to use this graph to determine which points between -1 and 5 the function is not continuous and when it is not differentiable. So go ahead and pause this and give it a try. All right, hopefully you have tried this one. So I want to find where I am not continuous and where I am not differentiable. So where am I not continuous? I only have one place that I'm not continuous. It's right here at the point 4. I have a jump discontinuity. So I am not continuous at the point x equals 4. And by this theorem, right, it says if I am not continuous, then I am not differentiable. So because I am not continuous at this point A, I am also not differentiable at x equals 4, since I am not continuous. Okay, that's the only place where I'm not continuous, but where else am I not differentiable? I want to find a point where I am either have a vertical tangent line or have a corner point. Well, I have a corner point right here at x equals 2. I have a different slope coming from the left side and the right side of 2. So the point x equals 2 is not differentiable because I have a corner point there. Even though I am continuous at x equals 2, I am not differentiable there. Well, I hope you guys had as much fun as I did during this lecture today. I really do think that this stuff is a lot of fun. So hopefully you caught on to that a little bit. And I hope to see you in the Zoom sessions if you have questions. Otherwise, I will see you later. Have a wonderful day.